Okay, so we're gonna solve an example of the designs of springs, similar to one that we were using, that we're doing in the class. So it reads, design a compression spring with plain ends using hard drawn wire. The deflection is to be 2.25 inches when the force is 18 pounds and to close solid when the force is 24 pounds. Upon closure, use a design factor of 1.2 guarding against yielding. Select the smallest gauge, Washburn and Mohn wire. So the first thing that we can find, so the design, it's asking for a design of a compression spring. So basically the questions for this are, what is the diameter of the coil? What is the diameter of the wire that I'm using? Obviously with these two I can calculate the spring index. What is the spring constant or the spring rate of the spring? And things like the solid length when it's completely compressed or the free length when it's not under any loads. And what we're gonna check to see if our design is good is, for example, that the number of wires, the number of coils is between 4 and 12, okay, or that that the spring index is between 1 and 12. So spring index between 4 and 12, 4 at 1, and that the number of coils is between 3 and 15. And obviously we could check things, for example, the natural frequency of the spring, but in this case we're not told that it's going to undergo fluctuating stresses, so that's probably not that important. But also we can check for buckling, right? So K is one thing that I identify right away. I can calculate pretty easily because we have the deflection of 2.25 when the force is 18 pounds. So basically with that I already have that my K, if F is equal to K times the deflection Y or deflection delta, however you want to see it, K is going to be F over delta. And the force is 18 pounds when the deflection is 2.25 inches. So this is an L. This would be 18 divided by 2.25, which is 8 pounds per inch. Okay, so I already have that, and it's not going to change regardless of my decisions as the designer of the spring. So that's pretty fixed. Now the other restriction that I'm told here is that the force should be 24 pounds for closed solid. So to reach that solid length, the force is 24 pounds. And I'm going to use a design factor of 1.2. So what that means is my design factor, which is going to be 1.2, has to be the yield strength in shearing over the maximum stress, which I know is the shearing stress, that's why it's a tau for compression springs, and I also have an expression for that. So from this I can just write it as tau max times the design factor is going to be equal to my yield shearing yield strength, right? So I have an expression for this, and I know that to find the yield shearing stress, it's going to depend on the ultimate strength, and that ultimate strength is going to depend on the diameter. So I'm going to write this equation in terms of the variables that I have for this problem. So I have that my maximum shearing stress, which is the correction factor, times 8F, in this case the F max that I'm giving, times D over pi d cubed times the design factor N has to be equal to the shearing stress. And for that I'm going to have a fraction of the ultimate strength, and the ultimate strength is given by A over dm. So ultimate strength is a function of the diameter, and that's one of the things that I'm going to choose for my design. The A and the M coefficients depend on the material that I'm using. So for this one, it's telling me that I have a hard drawn wire. Okay, so we'll look at those in just a second. And the fraction of the ultimate strength, this fraction f of the ultimate strength, is also given by the type of material I'm using. So from the tables that we saw in class, I know that the fraction of the ultimate strength for cold drawn metals, cold drawn steels, is 0.45. And this is from the table that tells me before and after the preset, and in this case there's no preset because we want to avoid yield. That's exactly what the problem is telling me. And then the coefficients A and M are going to come from the other table that lists A and M coefficients for SUT equals to A over D to the M, right? So for cold drawn, we have an A coefficient of 140 kips inch, so that's going to be 140,000, so that I just have pounds and I can compare it to this force. And M is going to be 0.190, right? So I have A, I have M, D is going to be my decision, I have F, N is equal to 1.2. The diameter of the coil is also my decision, same with the lowercase d. For the given maximum force is 24 pounds, and then KB is going to be a function of C, which is the spring index. Okay, so KB, now the one that we're using, you can use other, don't forget that, but the one that we're using for the correction factor is 4C plus 2 over 4C minus 3 times F, and I want to write this not in terms of D. I don't want to have D as a variable, but C, the spring index. And this is pretty common for all of the design problems. We'll substitute a capital D over D as a C. So it would be, force max times C. That C would take care of 1D up here and 1D in the denominator. So divided by pi D squared instead of cubed, because the C already has another D in the denominator, times N equals to 0.45 A over D to the M, right? And I have two variables here. First ones are C. C is not given. It's something that depends on the design that I want, and lowercase d. Okay, so here and here. Which one is easier to solve for? So the C is inside the parentheses here, and in the numerator and the denominator. So solving for C, having an expression C equals to something in terms of D is going to be too complicated. So I'm going to guess what the value of C is, so that when I'm solving in this equation, I'm solving for D, which is way easier. But also, so that's the first reason. And the second reason is because I don't have any restrictions for D so far. D could be anything. Like, I don't know, a micron, I don't know if that's going to be possible, but I don't know what the range is. As opposed to C, which I already know has to be between 4 and 12. So I'm going to do something different than the book, just so that you see how the iterative process changes and how any guess is a good first guess. So I'm going to assume that C is equal to 8. Why? Because it's right in the middle between 4 and 12. Okay, and I'm going to solve the problem using C equals to 12. To 8, sorry. And I'm going to solve for D from that previous equation. So it would be basically the same, 4C plus 2, 4C minus 3, 8 F max C times N over pi. I'm going to move that D squared to the right hand side, and I'm going to move the 0.45 on the 8 towards the denominator on the left side, to that denominator, so 0.45 A. Okay, and that would be equal to D squared over D to the M, right? Which would be D to the 2 minus M, Okay, and if I'm solving for d, it would just be the left hand side of the equation divided, or to the exponent of 2 minus m in the denominator, right? And that would be my expression for d. So I can write something like this in Excel. I can have my, I just do the calculations quickly, you don't need to do this, but I have, for example, here my 12. I can substitute that by an 8. Okay, and I already have written that equation for the theoretical d in this cell. So if I have an m equal to 0.19 from the table, 140, k is high, I'm now changing it to pounds. The force is 24, the maximum force, the design factor is 1.2, and the c that I am assuming is 8. So my theoretical diameter from that equation that I just showed you here would be equal to, sorry I missed it, 0.824. 0.824, right? This is theoretical because I'm probably not going to get out 824 inches from the available Washburn and Mohn wires. Okay, so what is the smallest gauge I can get that works for this theoretical diameter? Go to Google. I Google Washburn and Mohn steel wire gauge, first link, and I see this, and I'm looking for numbers here that are that give me that 0.824. 0.824 would be for the 13 gauge. So I cannot click on this, but whatever. If you look at the 13, you would see a 0.83 for the 13 and 3/4, which is slightly higher than what I got. Oh, there you go. So that one works. The bottom one, 0.80, wouldn't work. Okay, so the 13 and 3/4 gauge would work, and the real diameter would be 0.083. So I write that down. So my 13 and 3/4 gauge would be 0.083, and I'm missing something. So yes, this was a 0.08. Sorry, I missed this. Theoretical one had an extra 0 in there. 0.824. Okay, so since this one's slightly larger, that's gonna work. And I could actually see, like, now that I know what the diameter could be, I could go back to this equation and solve for n, so that I would already have everything. Actually, this one, I have c, I have d, I have everything, and I can solve for n. So I could go back here and solve for n and find that n is 1.215, close to that, and that's fine because I wanted it to be 1.2, my design factor, so my factor of safety being 1.215 is fine. So up to that point, everything's working fine, but I have some restrictions. So the C is fine for now, but I want to know how many coils I would need for the spring to be manufactured and have that K. So my spring constant is given by d⁴, the shear modulus, an 8 diameter cubed, and the number of active coils, right? Basically, if I already have the K, which was the first thing that I did, I can solve for the number of coils. So the number of coils would be d⁴ g over 8k d⁵. And again, I don't want this in terms of capital D because I don't have that yet. I would write it in terms of C. So d g over 8k c⁵. The c⁵ would take care of d⁵ and 3 of these lowercase d's. So that's why I only have 1 here. Okay, so this, in terms of the numbers I have, would be my real diameter. So I'm going to write those values down here. The one for the gauge wire I selected, the shear modulus. So we can look that up, the cold drawn steel from the second table that I used in class. that would be, write it down here, so 11.5 times to 10 to the 6th, so 11.5 times 10 to the 6th over 8. The k that I found was also 8. It's the first thing I did. Okay. 8, and c, which I'm assuming was 8 up to this point, would be an 8 cubed here. Okay, that k, again, I just wrote an Excel spreadsheet for that, so I'm using the real diameter, the shear modulus, and the spring constant 8, I get a number of, I get a number of 'number of coils would be 28.93. And obviously that is not within this range that I wanted. It's way more than the 15 I want. So how do I bring that number down? So my whole assumption for this, to solve for D, was that C was equal to 8, between the 4 and the 12 that I mentioned before. So I need to change C. Do I increase it or do I decrease it so that the number of coils goes down? So if the number of coils depends on C, the denominator, to the third, I need to make C much larger so that this number goes down. Okay? And it's by a lot, because I don't want it to be 28. I want it to be at a maximum of 15. Okay? My upper limit here is 15. Okay? So what I'm going to do is now assume that C is not 8, but C is 12, right? And I use the same equations. So I would use this equation again, only using a different C. Instead of 8, I would use a 10. So I could go to my Excel spreadsheet, see if I can fix this. Well, I actually don't know how to do it. So 12, enter, and now I get a theoretical diameter of 0.100. So my theoretical diameter, this one right here, would be 0.1001 or something. Go to my table and I find that 12 and a fourth well, 12 and 1/4 is 0.102, and that works. 0.102. So for 12 and a fourth, this gives me a real diameter of 0.102. Anything lower than that wouldn't work. With that diameter, I go back to this equation for the number of coils, with this D right here, and my new C being 12, and I get 10.6 turns. Okay. Do I need to round this up? I really don't, because I can always make 0.6 of a turn, like 3/5 of a last turn, right? Especially in this case where I'm just using compression spring with plain ends. If I was like grinding it, or squaring the ends, maybe I would have some restrictions, but especially not here. I can always make 0.6 of a turn, so that works. So this number is also within the range that I wanted, 3 to 15 for NA. Okay, so I'm okay there. And now I can calculate other things just to describe my spring better, my spring design better. So far I know that C is equal to 12, that NA is equal to 10.6, that my diameter is 0.102, which is the 12 and a fourth gauge. This is inches. with C and D, I can find capital D. So if C is equal to capital D over lowercase d, then capital D would be equal to C times D, which is 1.224 inches, right? And there's two more that are very important, the solid length and the free length. So the solid length would be the number, when it's fully compressed, I can use the table that I showed in class, but this is pretty easy. So when it's fully compressed, it's going to be the number of coils, 1, 2, 3, times the diameter, plus one more diameter. So this distance from here to here would be the number of coils, which is 10.6 times the diameter, which is 0.102 plus one diameter. Okay, or you can follow the table, the equation from the table, D and T plus 1, which is the same thing, 0.102 times number of turns plus 1, and that gives me a solid length of 1.184 inches. Now the free length is just going to be however much the deflection is plus the solid length. So when I compress it fully and release, it's going to, the solid length plus the deflection delta is what would give me the free length, right? So to do that, I need to know this deflection. And so if 24, if the F max is what brings down the spring to the solid length, I can calculate that deflection as F over K. So 24, and the spring constant was 8, this is 3 inches, and therefore the free length is the solid length plus my deflection. So 1.184 plus 3 inches. Okay, and I am fully describing my spring design. So I have the diameter of the wire, the diameter of the coil, the number of turns, what the solid length would be, and what the free length would be, right? The last thing that we check for, and we'll go over this in class later, is buckling. So I mentioned I'm not gonna test for the natural frequency, but I do need to make sure that when I'm compressing that spring is not gonna look all buckled. Okay, has to be straight when this is being compressed. And to do that, we're gonna use an equation again. We'll go over this in class later, but basically what we want is that the free length is lower than 2.63 d over alpha, with alpha taking 4 different values depending on the boundary conditions. So it can be 0.5, 0.707, 1, or 2, depending if the ends are fixed, for example, or fixed hinged, or both hinged, or just both free. So let's say we're using fixed. So for fixed, this value would be 2.63 over 0.5, and my capital D was 1.224. I run this value and I realize that this is in fact higher than my free length that I just found here as 4.2. Okay, so 4.184 inches is in fact lower than this value right here. Okay, it's going to be way higher than 5. So the fact that my free length was lower than that makes sure that there's not going to be buckling under compression.